Hi, I'm Norman Wildberger. We've been looking at the symmetries of the Platonic solids, these 5 remarkable objects that go back to antiquity. In our last video, we had a look at the tetrahedron and some canonical objects sort of sitting inside it. Today we're going to do the same thing for the cube, and I'm going to leave to you the exercise of doing a corresponding study for the octahedron, which is the dual object to the cube. Okay, so let's have a look at the cube. Very familiar object for us. Here it is. It has 8 vertices, it has 6 faces, and it has 12 edges. Now these 12 edges give us 24 directed edges. A directed edge being a situation where we take a vertex and an edge containing that vertex. You can think of that as a little vector emanating from a vertex along an edge. There are twice as many directed edges as there are edges, and that gives us 24 rigid motions because any particular directed edge can be sent to one of the other 24 directed edges, and such a rigid motion is completely determined by where that directed edge goes. So we know that there are 24 rigid motions, and we've already looked at exactly what they look like in terms of various rotations. Rotations about vertices, or about edges, or about essentially faces. Okay, so these symmetries, of course, they permute the 8 vertices and the 6 faces of the cube. And they correspondingly permute the 6 faces and the 8 vertices of the octahedron. But surprisingly, there's also not just 8 and 6 and 12-fold symmetry in the cube. There's also 2-fold, 3-fold, and 4-fold symmetry inside these objects. These are sort of simpler kinds of symmetries, more basic, more elementary things that we can find inside, say, the cube. So that's what we're going to look at today. We'll start off with 2-fold symmetry. What way is there a 2-fold symmetry about the cube? Well, in fact, we've already investigated that. Inside every cube there are 2 tetrahedra. In fact, when we were studying the tetrahedron first, that was sort of one nice way of obtaining it as 4 particular vertices of a cube. Say these 4 vertices right here form a tetrahedron. But that leaves 4 other vertices, namely these 4 vertices. They also form a tetrahedron. And there's exactly 2 such tetrahedron inside the cube. So here in this picture, with the cube oriented in a fixed position here, we see a green tetrahedron consisting of the points A, C, F, and H, and then a red tetrahedron consisting of the other 4 points B, D, G, and E. And we note that every face diagonal, so every diagonal of a face, say of this top face here, there's 2 diagonals, that one there and that one there, and one of them belongs to the green tetrahedron and the other one belongs to the red tetrahedron. And that's true of every face. Every face has 2 diagonals, and one of those diagonals belongs to the green one and the other one belongs to the red one. And in fact, once you know a single edge of the tetrahedron, then that determines the tetrahedron completely, because then you know the 2 vertices that are contained in it, and then the opposite sort of 2 vertices must be determined. So every vertex belongs to one tetrahedron and determines it. So for example, this vertex here, A, determines the other vertices in that tetrahedron, C, F, and H. So this is a beautiful 2-fold symmetry inside the more complicated symmetry of the cube. There's just these 2 objects playing a symmetrical role. This is a good point for me to introduce a little bit of graph theory terminology. So it turns out that when we're studying the Platonic solids, a graph theoretical point of view is very helpful and sheds light on some aspects of the Platonic solids. In fact, it is possible to study them purely from a graph theoretical point of view, as we'll show you later on. In particular, there's an interesting concept of a bipartite graph, which is very relevant to the story of the tetrahedra inside a cube. Okay, so let me review what is a graph from a sort of combinatorial point of view. Usually we think of a graph as something that we write down on a piece of paper. It's a picture involving vertices and edges. But mathematically or conceptually, it's probably better to think in terms of a set theoretic sort of framework. So a graph officially is a finite set V of objects. And when I say objects, I mean mathematical objects that we've already established, called vertices. So we're going to call the elements of this set V vertices. And they're just abstract objects of some kind or another, together with a finite set E of two sets from V, called edges. So for example, in this situation here, the vertex set consists of the letters A, B, C, D, E, F, G, H. So we're assuming that we have mathematical objects which are these letters. Now, you might ask, well, what is a letter? That's a very good question. But if you don't like letters, you could also substitute numbers. Okay, so instead of the letters A to H, you could have the numbers 1, 2, 3, up to 8. That would be a completely equivalent way of proceeding, and which is maybe a little bit more naturally solid. But if you're happy with the letters as being our objects here, then this is our vertex set, and the edge structure is determined by this set E. And the elements of this set are themselves sets. There are two sets from V. That means that they're sets with two elements, whose elements are actually from this collection V. So this particular graph, which we recognize is really the graph of the vertices and edges of the cube. So for example, if I show you this, perhaps close up, maybe like that, perhaps you're seeing something, well, okay, maybe you're seeing something like this. Okay, so for example, what we draw here, this edge AB, is really represented by the set AB. And notice that I use my convention for sets, which is that there's only spaces between objects, not commas, because they're unordered. And similarly, the whole collection itself, or the whole set of two sets, is a set, so it's also unordered. The actual order of these things doesn't matter, and so we represent that by having spaces between the objects. So this graph, which is of course very familiar to us, we're used to compressing information visually. This is a very efficient way of representing it. This is a more cumbersome, laborious way of representing things. But a computer would find this much more amenable. The computer just lists these sets, and there they are. While getting a computer to sort of assimilate this kind of information and to recognize that if we change the shape of things and then replace this edge EF with an edge going this way, that's still the same, that's more problematic. This is kind of a person-oriented idea. This is a more computer-oriented idea. And not surprisingly, the official mathematical definition is sometimes better expressed if it's closer to the computer point of view. Okay, so here's an example of a graph. It's actually the vertex edge graph of the cube. All right, good. So each of the 5 Platonic solids, we can draw a graph for it, okay, where we just label the vertices and the edges according to whether the actual object has edges between two given vertices. And the actual position of things on the page isn't really that important. Officially, the only thing really that matters is the set of vertices and the set of connections. So each one of these is just a representation of the graph. Here's the tetrahedron, here's the cube, here's the octahedron, there's the icosahedron, and there's the dodecahedron. So for example, for the dodecahedron, we can see face there, and around it there's 5 pentagonal faces, and around those there's sort of another 5 pentagonal faces, and there's sort of one pentagonal face at the back, so it's opposite to this one. Well, in the picture that would be represented sort of by the outside of this diagram. if we wanted to actually assign a region to that face. In fact, that's true of all of these. So this is a cube. There's their face there, and then there's the four faces around the front one, and then the face at the back is represented by the outside of the diagram. All right, so these are very pleasant and important planar graphs associated to the 5 Platonic solids. Now there's a special kind of graph called a bipartite graph that I want to define. So a bipartite graph is one whose vertices V can be partitioned into two disjoint subsets, say V1 and V2, that have the property that every edge of the graph connects one element of V1 with one element from V2. Okay? That's a bipartite graph. And visually it means that you can, say, color the vertices in two different ways, say with a red color and a green color. So each vertex is either green or red, in such a way that every edge goes from a red vertex to a green vertex. There are no edges from red to red, and there are no edges from green to green. Always only from green to red. So for example, this is an example of a bipartite graph. And I've shown you it explicitly. There's green, red, green, and so on. And I have purposely created such a situation where there's edges only from red to greens. That's a bipartite graph. Now here is our graph of the cube with a familiar labeling A, B, C, D, E, F, G, H. And we can see that this is also bipartite because we can make A red, B green, C red, D green, and then E green, F red, G green, and H red. And in this way, all of the edges join reds to greens. So that's a bipartite graph. And here's actually the official partition of the vertex set into the set ACFH, ACFH, these are the red ones, and the other ones BDEG, which are the green ones. Okay, so here's a little exercise for you. There are a few exercises in this lecture today. So the first one is to show that the cube's vertex edge graph is the only bipartite one amongst the Platonic solids. There are 5 Platonic solids, but only one of them is a bipartite graph. And that's this one right here. And I hope that you can see that this partition of the vertex set really just corresponds to the two tetrahedra that we had. That one tetrahedron consists of one color and the other tetrahedron consists of the other color. So the existence of this twofold symmetry amongst the tetrahedrons is really a reflection of the bipartite nature of the cube's vertex edge graph. The existence of these two tetrahedra inside the cube gives us a notion of parity of rigid motions of the cube. Because if we have a rigid motion of the cube, say this one here, we can ask, what is it doing to the two tetrahedra? There's only these two tetrahedra. So every rigid motion is going to do either one of two things. It's either going to fix the two tetrahedra. In other words, the red tetrahedron is sent to the red tetrahedron, perhaps permuted, but still sent to itself, and the green one is sent to itself. In other words, the two tetrahedra stay in their positions, even though they may be rotated inside their positions, but they stay where they are. Or the two tetrahedra interchange places. The red vertices move to the green ones and vice versa. Those are the two possible things that can happen because there are only these two tetrahedra floating around. And so we define the rigid motion to be an even one if the two tetrahedra stay where they are when we apply that rigid motion. And we say that the rigid motion is an odd one if the two tetrahedra interchange places. Okay, so here's your second exercise. Determine which of the rigid motions are even and which are odd. Okay, and then your next exercise, explain why even followed by even is even, while even followed by odd is odd, and odd followed by even is also odd, while odd followed by odd is even. In other words, when we're performing more than one rigid motion, if we perform one rigid motion and then followed by a second rigid motion, what we're saying here is that if we have an even motion to begin with and then followed by another even motion, then the result of that is another even motion. While if we start with an even motion followed by an odd motion, then together the cumulative rigid motion is an odd one. And our convention here is that we're going to read the order of rigid motions from left to right, like we generally like to read. So this means do this one first, then do this one. Right, so there's a nice thing to think about here just in terms of what happens to the two tetrahedra. Okay, now threefold aspect of the cube. We've talked about the two tetrahedra inside the cube. Now we're going to talk about the three face diameters of a cube. Here's a cube. Here is a face. Down here is the opposite face. And there's a line segment joining the center of this face to the center of the opposite face. And that segment we're going to call a face diameter. It's a diameter of the cube because it goes through the center of the cube. Okay, so the segments joining the centers of opposite faces are the face diameters of the cube. And there are three of them, because there are three pairs of opposite faces. There's top and bottom, front and back, and left and right. So there are three face diameters. And these three are segments which are all perpendicular to each other. I hope that's clear. And they obviously meet at the center of the cube. So these are like three perpendicular axes, if you like, through the center of the cube. And give some thought to this, that any rigid motion of the cube permutes these three face diameters. If we take the cube, perform any rigid motion, then the three face diameters get moved around. Maybe they stay where they are, but always a face diameter goes to another face diameter. We never get a situation where a face diameter goes to something different. And show that the face diameters are also the transversals of each of the cube's tetrahedra. So we were talking in our last video about transversals of tetrahedra. So if we take one of the tetrahedrons inside the cube, that this thing has transversals, and that these are exactly the transversals of each of the tetrahedra of the cube. There's also a fourfold aspect to the cube, which is very important. And that's given by the four vertex diagonals of the cube. What is a vertex diagonal? Well, these are diagonals of the cube through pairs of opposite vertices. So if you take two opposite vertices and just look at the line segment joining them, that is a vertex diagonal. It's kind of a long diagonal of the cube, the longest line segment contained inside the cube. And there are four of them. There's that one, there's that one, there's this one, and there's this one. You can see them here in this picture here. And of course, they also all meet at the center of the cube. These all pass through the center of the cube and are permuted by any rigid motion of the cube. You have any rigid motion, and it's going to move these four vertex diagonals around. Okay, now we come to an interesting exercise for you, rather important one, that each rigid motion of the cube gives exactly one of the 24 permutations of the four vertex diagonals. If we have four objects, then there are 4 factorial, or 24 different ways of rearranging them. Now we also know that there are 24 different rigid motions of the cube. Because I remind you, the cube has 12 edges and so 24 directed edges. Okay? So there are 24 rigid motions of the cube. There happen to be 24 permutations of the vertex diagonals. And given any rigid motion, it's going to give you a permutation of these 4 vertex diagonals. And what we're saying here is that, in fact, this sort of correspondence between rigid motions and permutations of these 4 diagonals is faithful. In other words, every rigid motion gives a unique permutation. If you know the permutation, you know the rigid motion. So this is showing that the group of rigid motions of the cube is algebraically the same as S4. S4 is a symmetric group on 4 objects. We talked about S3 last time, so this is going up a little bit in complexity, but the algebra is similar and gives us a very concrete control of the geometry or the algebra of these rigid motions. So give this some thought. It's great to have a model of a cube in front of you and play around. See how the various rotations around vertices, faces, and edges, how they act on these 4 diagonals. Excellent exercise, kind of introductory thing for group theory. Okay, so that's really good. We've established the 2-fold, the 3-fold, the 4-fold symmetry sort of inside the cube by actually finding canonical structures inside here. Maybe not entirely obvious. You have to kind of look to see whether there's some patterns and structure inside. I'm going to leave the corresponding investigation of the octahedron to you. We know that the octahedron is dual to the cube because the centers of the faces of the cube form an octahedron, and correspondingly the centers of the faces of the octahedron form a cube. So rigid motions of the octahedron and rigid motions of the cube, they're pretty well the same thing. So there should be corresponding sort of objects in the language of the octahedron. In our next video, we want, of course, to go up to the dodecahedron and the icosahedron pair and ask the same kinds of questions. What happens if we look inside the dodecahedron? We happen to know there are 60 rigid motions, and we've actually looked at what kinds they are in terms of rotations. But now we'd like to say, well, can we find things inside the dodecahedron that, that sort of allow us to understand these rigid motions perhaps in a simpler way? So sort of in the same direction as we're doing here. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.